So this IC is initially has been brought up by Jack Kilby and Robert Noyce, okay, who received the Nobel Prize in the year 2000 in physics for their invention of integrated circuits. Okay, so in the 1960, this invention has been taken place, and the first type of technology came into existence. That is nothing but the SSI, small scale integration. So this small scale integration specifies that we have the possibility of grouping up to maximum of 10 number of gates, so that we can satisfy different type of logical gate circuits. Okay, a NOT gate, a NAND gate, a NOR gate, a AND gate, a OR gate can be realized. Okay, so these 10 number of transistors can be placed into a single IC chip, and that type of technology it is called as SSI. This came into existence in the year 1960. Then still advancements are continuously occurred. So in the 1970, MSA technology came into existence. So there, the number of transistors that have been incorporated within the IC chip has been increased to thousands. Okay, so if you are able to incorporate as many number of transistors possible within the IC chip, then proportionately we have the possibility of increasing the different type of applications. Due to that, in the MSA technology, then by grouping different type of transistors, then the other functional modules such as adders, subtractors, multipliers, dividers, encoders, decoders, multiplexers, demultiplexers, all into came into existence in the MSA technology. Then after that, in the 1980s, okay, LSI technology came into existence, where LSI stands for large scale integration. Then this technology, it is the basis for the invention of microprocessors. Okay, so microprocessor, the first microprocessor came into existence is 4004. It is a 4-bit microprocessor. 4-bit microprocessor means we have the possibility of performing the arithmetic or logical operations upon this 4-bit data. Okay, so then after that, later so many other advancement came. So the next technology is 8080. It is a 8-bit microprocessor. Okay, so that we have the possibility of producing or implementing the other type of mathematical operations very easily. Okay, then 8085 also came into existence in the same LSI technology. Okay, then after the advancement of 8085 is 8086. It is a 16-bit microprocessor. Then after 8086, 80286 came into existence. It is also a 16-bit microprocessor. Then after that, 80386 came into existence. It is a 64-bit microprocessor. Then 80486, then 80586. 80586 is also called as a Pentium processor. Okay, so that Pentium process came into existence in terms of very large scale integration technology. Okay, very large scale integration. Then after that, so many advancements again takes place. So P1, P2, P3, P4, P5. After that, Intel process came into existence. I1, I2, I3, I4, I5. Now presently we are in the generation of I10. Okay, so much of advancements have been taken place. Okay, so mainly this advancement, the difference in between all the different type of technologies is the transistor size. The features that are being more concentrated are the transistor size, the speed of operation, power consumption, and the reducer cost. Okay, all you know about this one. So size of the transistor. Okay, previously it was in terms of millimeters. It has been still reduced to the micrometer range. Now presently we are using the transistor size in the nanometer range. The size has been very much shrunk by the advancement of this technology. Then proportionately, the next feature that we are concentrating is the speed. Okay, the speed will be more in order to switch from logic 0 to logic 1 state, or logic 1 to logic 0 state. Okay, this ability will be very much high, or speed will be high when we are considering the IC chip. Whereas if I am considering the passive component circuit, then the speed will be very slow. For that purpose, we are preferring the ICs. Then the third feature that we are able to concentrate is power consumption. Okay, so physically, if you are able to make the circuit, so many type of active and passive components will be required. Okay, thereby power consumption will be there, power dissipation will be there. Then in order to avoid that, if you are able to place all that similar type of components into a single IC chip, then thereby the parasitic capacitances, parasitic resistance will be very small. Due to that, the power consumption will be very much reduced. Then the reducer cost. So individually, if you are purchasing a single component and if you are able to fabricate or if you are able to make one or if you are able to design one type of circuit, then the cost will be more. Whereas all that components are being embedded on a single IC chip, then if that IC cost will be very less. Okay, so all these are the features of the ICs. Okay, so Moore's law it is there. Okay, Jordan Moore, he is a co-founder for the Intel Corporation. Yeah, in the 1970s itself, by seeing the different advancement in the technology, he proposed one Moore's law. What it specifies is nothing but the number of transistors that will be incorporated on a single IC chip will be doubled for every 18 months of duration. It has occurred. It has occurred practically. It has occurred practically. Okay, we can observe here in the 1996, VLSI technology was in existence, where Pentium 1 processor came into existence. Okay, in that about 5 million transistors are being incorporated. Whereas in terms of mid 1997, 10 million number of transistors are being incorporated within the single IC chip. Whereas coming to the 1999, 20 million transistors are being incorporated. Then due to that, this Pentium 4, if I'm able to take an example, which came into existence in the year 2001, in that about 43 millions of transistors are being incorporated in a single IC chip. Okay, just you can imagine within a 2 centimeter by 2 centimeter workspace of area, 43 million number of transistors are being incorporated. Then what will be the size of each transistor? It will be in terms of nanometers. Nanometers is very thin with respect to our human hair also. Okay, so that much of advancements has been taken place, and it has been specified in the 1970 itself by Moore's law. Okay, then next we discuss about the VLSI design cycle. Okay, so here this flow chart we can consider. It specifies what are the different steps that are being involved in order to manufacture a single IC chip. Okay, the first step of design cycle is system specification. Okay, system specification is nothing but first we have to specify that for what type of application we want to make the IC. For what type of application we want to make the IC. Okay, suppose for example a simple adder circuit if you want to make the IC, a multiplier circuit we want to make the IC, or even a ALU we want to make the IC, automatic and logic unit we want to make the IC. Okay, so that specifications has to be given for what type of application we want to make the IC. Then along with the application that we want to produce, along with that some more features we have to clearly specify. Okay, what are the different features are nothing but what type of programming language we are able to use, whether we are using the Verilog programming or VHDL programming or any other programming. Okay, that has to be specified. That also comes in the specification itself. Along with that, the area requirement, how much of area should be required. Okay, so what will be the size of the transistor? Okay, what will be the aspect ratios? That all has to be specified. That comes into the specification. Then once the application has been decided, the next step of VLSI design is architectural design. This architectural design specifies that, suppose for example, if you want to design a ALU module. Okay, ALU is nothing but automatic and logic unit. Okay, internally it may be consisting of number of arithmetic modules. Okay, so arithmetic modules are nothing but it should be able to perform arithmetic operations such as addition, subtraction, multiplication, and division. In order to perform that addition, a one module, sub-module will be required. Similarly, in order to perform subtraction, one sub-module will be required. In order to perform one multiplication, one sub-module will be required. Okay, so how all these modules are being interconnected in order to form one complete architecture. So that is nothing but the architectural design. Similarly, a logical module if you want to produce. Okay, what type of logical operation we are going to perform, either the logical AND operation, logical OR, logical NAND, logical NOR, inversion operation, that all should be specified within the architectural design. Along with that, suppose if you are requiring the shifting operations also, shifting towards left, shifting towards right, all that shift, different sub-modules will be involved within that architectural design. Okay, then specifications include first what type of application we want to perform, then after that architectural design, what are the submodules that are been existing, then after that functional design. Okay, in order to make that adder, okay, what type of internal circuit we are able to propose. Okay, so that comes in the functional design. So we are dividing the entire module into submodules, and each submodule will be a functional module. Okay, suppose for example adder it is there, either it is a full adder or half adder. So if you are able to design an half adder, the next approach is logic design. Okay, how many number of AND gates will be required, how many number of OR gates will be required. Okay, that all will be specified within the logic design. Once a logical gate circuit has been designed, the next step of process is circuit design. Circuit design is nothing but each logical gate will be then converted into transistor circuit. Again, in the transistor circuit means we have to specify that whether we are able to use a BJT transistors or whether we are able to use MOS transistors. Again, in the MOS, whether the NMOS logic or PMOS logic or CMOS logic, or whether we are able to use BiCMOS logic. That all has to be specified, and it comes under the circuit design. Okay. Then after that, once the transistor circuit is also been produced, that transistor circuit then will be converted into the layout form. Okay, so that layout form is nothing but physical design. Once we are able to produce the layout, then this will be processed to the fabrication unit. There it will decide how to prepare that PCB with respect to the layout. Okay, then once that PCB, printed circuit board, is being prepared, then next is the packaging. Okay, so that has to be packaged. Okay, whether we are able to use the plastic package, whether we are able to use metallic can package, or whether we are able to use ceramic package. Okay, different type of packaging techniques we can adopt. This is the complete procedure. Okay, once again in the fabrication, when we are performing the fabrication, again it involves a different type of steps. Those are nothing but substrate preparation will be there, then oxidation process will be there, then photolithography process will be there, then diffusion process will be there, ion implantation process will be there, then metallization process will be there, and finally once the entire IC it is been prepared, then it is been sent for the packaging. Okay, all these are the design cycle steps that are being involved. Okay, this here individually it has been explained. Okay, functional design is nothing but what are the different functional modules that are being required and how they are being interconnected. It can be specified in terms of functional design. Then next is logical design. Okay, so logical design is nothing but once we are able to consider one functional module, what type of operation it is able to perform. Okay, for that we are able to form the analysis also. Okay, so that analysis, so it is nothing but we have to refer with respect to its truth table. Okay, so once these logical expressions are been obtained, then it can be easily converted into the logic diagram. That logical diagram can again be simulated by using either the VHDL programming or the Verilog programming. Then circuit design. Okay, what are the different modules are being required? So once if they are being interconnected, then we have the possibility of producing the net list. Okay, then once all these functional modules are being designed and they are being interconnected, finally it will be packed. Okay, then this will be called as a packaging. Okay, so all these dots or these square shaped dots that are being visible, all these will be considered as IO pads. Through these IO pads only, the external pins that are being visible for the IC, that will be interconnected. Okay, all these IO pads, its requirement is it avoids the amount of excess voltage not to reach to the particular logical modules. Okay, once that excess amount of voltage has been reached, then the entire structure that has been formed, it will be damaged. In order to avoid that, we are able to pass the inputs through these IO pads. Then the fabrication already I said that the fabrication includes the different steps: lithography process, then a deposition process, then diffusion process, and finally a chip will be fabricated. That chip will be then sent to the packaging in order to make one printed circuit board or a multiple chip module. Okay, finally this step of a full custom design, it is being produced. Okay, now here again two types of approaches are being possible. Okay, one type of approach is manually we can build the transistors, we can interconnect all the transistors and we can make one PCB. And due to the advancement of these ICs, one simplest technique has been found. That simplest technique is nothing but by performing the programming, we have the possibility of implementing the same type of application by using that particular IC chip, and that type of approach is called as ASIC. ASIC, application specific integrated circuit. What this application specific integrated circuit specifies is nothing but here we are able to program the different logical gates that have been available within the IC chip. By programming or by dumping one type of program into that particular IC chip, we have the possibility of performing that particular application. Again, this type of programming logic devices, PLDs, are being classified into different types. We can use either the PAL approach, we can use either the PLA approach. Okay, PAL approach specifies that programmable array logic. In that, programmable AND gates will be there, whereas OR gates will be fixed. Whereas in terms of PLAs, programmable AND gates followed by OR gates. Okay, both AND gates and OR gates have been programmable by using this PLA logic. Here, in terms of either the PAL or PLA logic, we are able to use AOI and or invert logic, or we can use OAI. Okay, or and invert logic. Okay, mostly AND gates and OR gates are being involved in order to implement any type of particular application. Okay, so this PAL and PLA logic can be used in order to implement some all type of applications. Suppose if you are going to implement one ALU unit, then this PLA or PAL approach cannot be suitable. Then we are going the advanced version. It is called as FPGA. Okay, field programmable gate arrays. Okay, so this will be the structure of FPGA. Okay, this is nothing but internal structure of IC integrated circuit. We will be having number of functional modules. All these square boxes that are being represented are being called as functional modules, and each functional module may be as simple as logical gate, or it may be other type of functional modules such as multiplexer. It may be a multiplexer, or it may be a flip-flop, or even it may be a encoder, decoder. Like that, different functional modules will be there that can be programmed by writing one program, whether we can use the Verilog logic or the VHDL logic. Then we can have the possibility of dumping that particular program into this FPGA. Okay, once if you are able to dump one particular program, a connection will be established from one logical module to the another, one logical module to the another, one logical module to the another. Like that, all that logical modules will be enabled, and finally it is able to produce the output. That output can be observed across any output pin. Okay, this type of technique is called as FPGA, field programmable gate arrays. Okay, so the features of this field programmable gate arrays are, so it will be having up to 300 IO pins. Up to 300 IO pins. Input output pins will be in the range of 300. And internally it supports 10,000 number of logical gates. 10,000 number of logical gates. Okay, again it satisfies both combinational logic and also the sequential logic. Okay, all these are the features. Okay, so another type of technique is also there in order to make this ASIC, application specific integrated circuit. That it is nothing but PLD. Okay, where this PLD is nothing but programmable logic devices. By cascading number of PLDs, we have the possibility of making one CPLD. This one it is. This is the structure. Number of PLDs have been cascaded. This will be considered as one PLD. It is being cascaded with another. It will be cascaded with another. It will be cascaded with another. Okay, number of PLDs will be cascaded in order to accept more number of inputs and in order to produce more number of outputs. And that type of structure is called as a CPLD architecture. Okay, so this kit represents a 3 starter kit. Okay, so this particular IC chip is called as FPGA. It will be considered as heart of the board. Okay, so surrounding to this one, the number of functional modules will be there. Okay, so buttons will be there, then LEDs in order to display the output, then DCD display will be there, then also the switches will be there in order to provide the inputs. Okay, so all these are the this functional module represents one FPGA kit. Now our purpose is in order to introduce you the LT Spice, where LT Spice is a programming technique. Programming technique, there we can have the possibility of performing the design and the simulation for any type of VLSS circuit. Design and simulation for any type of VLSS circuit. And the features of this LT Spice are, LT Spice stands for Linear Technology Simulation Program with Integrated Circuit Emphasis. Okay, all these are the features of this LT Spice. Okay, so it is having unlimited number of nodes. Okay, it has a schematic or a symbol editor, it has a waveform viewer, it has a vast library including number of active and passive devices. It has a fast simulation using the SNPS, switch on mode power supply. Okay, it is able to produce a transient response, it is able to produce a step response, and it is also used to observe the power computations also. All these are the features. Okay, then it is a free source that has been available. Okay, just you can download this software by using this link, www.linear.com/software. Okay, so this type of window will be appeared. Select this one, download switcher CAD LT Spice, then directly just by following the simple processing steps, we have the possibility of downloading this LT Spice. Okay, so once this LT Spice it is been downloaded, you can open that window. Then here the starting window will display all these type of icons. Okay, so as the name here itself it is being specified. As the time is less, just I am skipping these. What are the icons that have been shown here? In order to make our symbols will be there, a resistor symbol, a capacitor symbol, a diode symbol, then place component symbol, then rotate, move, then cut symbol, then duplicate symbol, then placing ground. All that symbols will be available within the toolbar itself. You have the possibility of using all the tools that have been available on the toolbar just by clicking the icons, or we can use this toolbar also. Within this window, all these tools will be available. Okay, that from there also we have the possibility of selecting the components. So it has I have said that it is having a vast library. So internally it is consisting of number of voltage dependent voltage sources will be there, current sources will be there, transistors will be there. Again in the transistors different types. Okay, BJTs will be there, mass transistors will be there, then inductances will be there, then MOSFET transistors will be there, BJTs will be there, then voltage control switches will be there, ICs. Some ICs are also been available within the library. We have the possibility of utilizing all that components. Okay, now I'm going to introduce you. So again by using this LT Spice, we have the possibility of performing several type of analysis. We can test for a transient analysis, we can check the small signal AC analysis, we can perform the DC sweep analysis, the noise calculation is also possible, then DC transfer function we can produce, and then DC operating point can be calculated. All these are the different type of analysis that have been supported by this LT Spice. Okay, so I will try to explain at least two type of analysis for one simple circuit. Okay. Once if you are able to install this one, that icon will be present. Then just you have to follow this procedure, very simple procedure. Okay, so you can perform the different type of projects also by using this LT Spice. Okay, so final year projects can also be done by using this LT Spice. Okay, you can perform the research also by using this LT Spice. Just you have to use this procedure, file, then new schematic. I am explaining you a simple application. We have the possibility of building any type of complex circuit. Okay, consisting of hundreds of components also. Okay, so if I am observing this toolbar, we are having one tool here, component. Okay, this component, if I am able to click this one, okay, so whatever the different components that have been available within the library, all will be displayed like this. Okay, so it is consisting of op amps are there, then resistors are there, capacitors are there, NMOS transistors, PMOS transistors, LEDs, all that will be there. Just by typing here what are the different type of components we are able to require, just select this one, it is able to produce one resistor, and by perform the selection of this one, okay, one resistor can be copied onto the screen. Okay, so if I'm able to use control R option, that resistor can be rotated, one resistor. Okay, just place this one by using the mouse. Okay, if you are not requiring the resistor, means just we can press the escape key. Now if I want to place the capacitor, the procedure is I can use this component, then within that component number of library files will be available. From that we can use or just click this, okay, a component can also be dragged like this. Okay, so one capacitor is enough. I want to form one low pass filter operation. Okay, here I am requiring one voltage source. Okay, for that purpose again I have selected the component. I had selected the component. In that I am selecting this voltage. Voltage here, voltage it is there. Now select this one. One voltage source can be placed. Okay. Once if we are able to place that voltage source, then one ground will be required. So I am making one ground connection. A complete circuit will be obtained. Now we have to interconnect. Here wire it is there. Just we can interconnect like this. Interconnect. Okay, drag from the corner point up to this another corner of the device. Okay, like this. Drag here. Just drag up to the node that you are able to connect. Like this. Drag here, then interconnect. Okay, node has been formed. Okay, now escape. By pressing the escape key, we can remove that wiring connection. Now we have to fix the values here. Just take the pointer onto the component, then just right click this one. Okay, or it is there. No, we can fix the value of this resistor 1k 1 kilo ohm. Okay, value has been changed. Now place the pointer upon this one. Now right click. Okay, so we have the possibility of giving the capacitor value also. I am giving 1 microfarad, U symbol, in order to specify microfarad. So 1 microfarad I had assigned. Now for this one, voltage, select this voltage, right click this one. Okay, so a DC value can be given within this window itself, or if you want to give in terms of sinusoidal voltage, then you have to select this advanced option. Select this advanced. In that, select as sine. A sinusoidal signal, you have the possibility to give. Okay, DC offset, here it is not required. I am giving just given as 0. Now I am giving the AC voltage as 5 volts, amplitude as 5 volts. Then frequency, suppose 1 kilohertz frequency I am giving. So no need to give the delay here. So I am placing the delay as 0. Then theta, phase difference are also 0. Okay. Then number of cycles. Suppose if I want to produce for 5 cycles, I am giving the number of cycles. N cycles is nothing but number of cycles. Okay, I am giving as 5. Okay. Okay. Now all the specifications are being specified here. Okay. So 5 volts signal with 1 kilohertz frequency. Now all that the values I have specified. Okay. Now I have to simulate this one. In order to simulate this one, run command, run option it has been available here. Just if you are able to place the cursor upon this toolbar, it specifies what type of operation that we can do. Okay, or we can go for simulate. In that run option it is there. Run. Okay, so we have to specify the stop time. Okay, I had selected 1 kilohertz as a frequency. Then what will be the time period? 1 millisecond. So if I am able to select the 5 millisecond of time period, then it is able to produce 5 cycles. Then the starting data I am selecting as 0. Okay, this is enough. Okay, so directly this type of window will be produced. Okay, it specifies that we are able to perform the transient analysis. In that I had given the time period as 5 milliseconds. Now observe this. This is the simulation window that has been appeared. So here it is showing as a black color because it doesn't show what type of response we want to view. Okay, now if I am going onto the circuit, now if I am placing the pointer near to the component, then it is called as a voltage probe. If I am placing the pointer upon the component, then it is called as a current probe. Okay, now I want to observe the voltage. Okay, so just click here upon this line and at the input side, it displays the signal. This is the input signal. Now I want to observe the output. Okay, for that purpose, I have to observe the output across capacitor. Okay, just place the pointer here. Then this is the output signal. So input signal is in the green color, output signal is in the blue color. Okay, like this we have the possibility of observing the transient analysis response. Okay, now the same circuit it is there. Same circuit it is there. For that, we want to perform the AC analysis. We want to perform the AC analysis. For that purpose, I have to cancel this. I have to cancel this transient analysis. Okay, I am erasing this one. Just I am using this cut symbol. Okay, scissor symbol. It represents cut option. Okay, so I want to cut this voltage source also, because in order to perform the AC analysis, I have to give the AC voltage. For that purpose, again go to the place component in that voltage. Now place the voltage. I have placed the voltage. Now for this, you have to provide the specifications. We want to give the AC voltage, not this DC value. For that, select as advanced. Okay, so here it is there, AC amplitude. Okay, suppose I am giving the AC amplitude as 1 volt and the phase shift as 0 degrees phase shift. Okay, now it is enough. Okay, for that purpose, you have to select as none, then AC amplitude as 1 volt. Okay, so I had given. Okay, now I have to perform the simulation. Simulate run option. In that, we have the possibility of selecting the different type of analysis here. We can do the AC analysis, we can do the transient analysis, DC sweep, like that. Okay, I am selecting the AC analysis. Okay, in that, the type of sweep we can select here octave or decade or linear. Okay, I am selecting this octave. The number of points that we want to select, I am giving as 100 points, and the starting frequency as 10 hertz I am giving, and final frequency as suppose 1000 or 10,000 kilohertz. Okay, starting frequency and ending frequency I am specifying. Okay, so with respect to the given specification, it is showing the window. Okay, so here also we want to display the AC analysis response. Okay, place this pointer at this end. This is the AC analysis. Very simple. Okay, this is the AC analysis. It is consisting of two curves here. This is the magnitude curve and this is the phase curve. Okay, so if you are observing the full. Okay, so it is acting as a low pass filter. All the higher frequencies will be filtered. Okay, suppose if you don't want to display this phase curve, okay, just click here, click on this y-axis, then in that don't plot phase, then the phase plot can be removed. Only the magnitude plot will be there. Okay, like this we have the possibility of simulating the circuit. Now going back to the circuit, again just by interchanging this resistor and capacitor, okay, we have the possibility of performing the high pass filtering option. Okay, any circuit. Okay, so suppose if you want to observe the response that is been available, the different type of models that have been available within this. Okay, so if I am selecting the op amps, okay, double click this one. This many number of op amps are available within the library. So hundreds of op amps are there. Okay, if I am selecting any particular op amp, open this in the macro model, means this circuit will be directly open. This circuit will be directly open. So what is this circuit? This circuit is an, okay, if I am providing the negative feedback here and I am providing the input to the non-inverting terminal, then it acts as a non-inverting amplifier. Okay, inbuilt number of modules are available. Okay, that also we can utilize. Now just if you want to observe the response for this one, output response, just use this run option. Okay, a window will be shown. I want to close this previous model. Okay, I have closed this one. Now enlarge this one. You have the possibility of observing the input and output. Just I am placing the pointer here at the input side, voltage probe. This is the input signal. I want to observe the output. Okay, place this pointer at the output end. This is the output signal. Okay, input I have given as 1.5 volts, plus or minus 1.5 volts. Whereas the output that we are able to produce It is producing the output in the form of plus or minus 2 volts. A non-inverting amplifier. Okay, this type of flexibility is been available by using this LT-Spice software. Okay, we can use the inbuilt models also. This is about my presentation with respect to the LT-Spice.
Yes, sir. Thank you, sir, for your nice presentation. I request the participants if you have any queries, please raise your questions. Yeah, one the student LE405 Mamata, how to install the software? She is asking how
Yes,
to
sir. Yes, sir.
install.
Yes, sir. So here I had specified very simple thing. It doesn't ask any type of complexities. Just use this. Use this link. http www.linear.com/software. It asks whether two versions are available again here. Okay, so whether it is a advanced 2016 version, it is there, 2021 version, it is there. Okay, 2016 version easily can be installed. It asks whether the version should be suitable for Windows 7, Windows 8, Windows 10, or XP Professional. That all it will ask. So select one option depending upon your OS that is been available. A direct simple steps will be there. No license key it will ask. Just you can proceed just by accepting.
Thank you, sir. Sir,
Okay, very simple.
actually in AC analysis, so you have shown the frequency response of the circuit diagram.
Yes, sir.
Yeah. So we can also see the output response. No?
Sir?
In AC analysis, so you have shown the frequency response of the circuit.
Yes, sir. Yes, sir.
Yeah, we can also see the output waveform.
Output waveform means we have to go for the transient analysis, sir.
Oh, in the transient analysis, only input and output.
Signals will be displayed.
In AC analysis, only we are going to
only
find
response.
the frequency response of the circuit
yes,
diagram.
Sir. Magnitude plot and phase plot we can view.
Okay, so that's
so for that purpose only we are having the different type of analysis, sir. So similarly, DC analysis is there. Okay, only DC type of response we can view. Okay, depending upon the selection of the input, sir. If I am giving the AC signal, then we can view the depending upon the AC signal. If I am giving as input, then I can observe AC analysis. If I am giving the input in terms of frequency signal, then I can perform the transient analysis. If I am giving the input in terms of DC voltages, then we can use the DC analysis.
Okay. Thank you, sir.
Okay, sir.
So the students they can utilize this software.
Yes.
Please.
Yes.
Sir, good evening, sir.
Good evening. Please speak.
Subramaniam, ask me.
Sir, why, sir, in our India we can't find any manufacturing industries like microprocessors?
So we are not having any fabrication unit up to now. Okay. So generally, if you are able to observe in terms of California is the largest manufacturing plant. Okay. So there the number of ICs that are being manufactured, okay, practically it has been mentioned. So that will be more with respect to the rainfall they are observing in that particular state. So that many number of fabrication units will be there. In India, we are not having any type of fabrication unit. If fabrication units are there, then directly ICs can be fabricated. Only assembling units are there. We have the possibility of collecting the different ICs from different countries. Then we can assemble all the different ICs, different type of components. We can make different type of applications.
Yeah, Subramaniam, is it clear?
Sir.
Yeah.
Sir, okay, sir, clear, sir. Then what?
Go ahead.
Why India is lagging in the fabrication techniques, sir?
Yeah, that is only the technology transfer and investment, and the government has come forward and give the permissions, those who come forward to establish. Right? The main is the technology. We require machinery to have the large scale production. Okay, we supply the raw material to other countries, and again we'll buy the components from the other countries. Okay, the government is now thinking to establish the manufacturing units. Yeah.
Yes, sir. The raw material is only for sand only.
Sand only,
Sand only,
silica
sir.
only, silica. So in that also again advancements have been taken place. Okay, germanium or silicon, those are the olden days. Now presently, FinFET technology, CNT FET technology, okay, all those technologies are came into existence. Then we have the possibility of using the carbon materials also. Silica is more available, it is cheap, so silicon products are more preferred now.
Yeah. Okay, Subramanya.
Okay, sir. Thank you, sir.
Yeah,
Okay.
yeah. Okay, fine. So thank you, sir. Thank you for all the students and faculty for supporting us. So we'll come back on Monday. Thank you, everyone. Thank you, sir.
Thank you, sir. Thank you.
Yeah.